The cabin was calm. Outside, the vast expanse of Western Australia stretched beneath the Airbus A330, unbroken and serene. Instruments glowed in the cockpit. Autopilot engaged, flight smooth. Then, without warning, the Serenity fractured. A sudden jolt. The nose of the aircraft dipped sharply. Alarms pierced the cockpit, a staccato chorus of warnings that demanded instant attention. The plane lurched downward, throwing passengers and crew alike against their restraints. Coffee cups tumbled, cabin announcements were cut short, seatbelts tightened by unseen hands. In the flight deck, pilots reacted with practiced urgency. Hands moved over the controls, eyes scanned instruments glowing red, brains calculating angles, speeds, and altitudes in seconds. Outside, the horizon tilted unnaturally, a reminder of the fragile line between normal flight and disaster. Minutes stretched like hours. Outside, the sun glinted off the wings, oblivious to the chaos within. The aircraft shuddered again, a violent reminder that technology, no matter how advanced, could falter. Inside, human skill, calm under pressure, and decision-making became the last barrier between safety and catastrophe. By the time the aircraft stabilized, injuries had occurred, adrenaline coursed through every body, and a chain of events had begun that would challenge assumptions about the reliability of flight systems, crew response, and aviation safety. This was Qantas Flight 72, and its story was just beginning. Qantas Flight 72 was a routine passenger service from Singapore to Perth on October 7, 2008. The aircraft, an Airbus A330-303, was a workhorse of the fleet, wide-body, long-range, technologically advanced. Its two Rolls-Royce Trent 772B engines hummed steadily, autopilot engaged, a machine built for precision and reliability. The crew were experienced professionals. The captain had thousands of hours in command, familiar with the aircraft's nuances. The first officer had similarly extensive experience and a reputation for meticulous attention to procedure. Together, they represented the human element of aviation, highly trained, disciplined, and accustomed to managing unexpected situations. Passengers settled into the long-haul rhythm. Some read, others slept. The cabin lights dimmed to create quiet comfort. Flight attendants moved efficiently, unaware of the unfolding challenge that would soon test every assumption about in-flight safety. The Airbus A330 itself was a marvel of modern engineering. Its fly-by-wire system relied on three air data inertial reference units, ADIUs, to measure airspeed, altitude, and angle of attack. These systems fed commands of flight computers, which in turn moved the control surfaces. Normally invisible, these systems work flawlessly, translating pilot inputs into smooth flight. But this reliance on automation, precise yet complex, would prove critical. Outside the aircraft, the night was calm, skies clear. There were no weather hazards, no turbulence, no visible threat. The environment offered no clue that within minutes, passengers and crew would confront a sudden, uncommanded pitch-down that would challenge both technology and human reaction. This calm before the storm framed the stage. A technically advanced aircraft, experienced crew, and a routine flight that would expose vulnerabilities in systems, procedures, and situational awareness. The Airbus A330-303 was designed for precision. Its fly-by-wire system replaced direct mechanical linkage with computer-controlled hydraulics, giving the aircraft smooth, predictable handling. Three air data inertial reference units, ADIUs, continuously measured airspeed, altitude, and angle of attack. The system relied on the consistency of these sensors to manage flight surfaces. In Flight 72, one Nadir began delivering erroneous data, a subtle anomaly invisible to routine monitoring but fatal in its effect. The Aircraft Flight Control Computers, FCCs, received conflicting inputs from the faulty Adiru. The computers, following their programmed logic, triggered protective maneuvers, sudden pitch-downs intended to prevent aerodynamic stalls. What should have been invisible safety automation became the very source of danger. Pilots, trained for mechanical failures and procedural deviations, were thrust into a situation where automation itself became adversarial. Crew experience shaped the response. The captain and first officer had extensive training in upset recovery and Airbus systems, yet the suddenness of the Adiru anomaly challenged ingrained expectations. Flight attendants face a human reality, securing passengers amid abrupt, violent aircraft motion. Passengers, caught in mid-motion, experienced the uncontrolled forces of the aircraft firsthand. The environment was benign but deceptive. Night over Western Australia offered no visual cues to counter the misleading instruments. Calm air, clear skies, and smooth flight reinforced the expectation of normalcy. There was no turbulence to explain the motion, no storm to blame. In this void of environmental warning, the fault was purely internal, hidden within the complexity of the aircraft systems. Systemic factors converged. The Adiru fault was rare, but not unprecedented. Procedures existed to manage erroneous readings, yet the speed and combination of events compressed the decision window. The crew had to interpret alarms, evaluate conflicting data, and execute recovery maneuvers, all in seconds. The aircraft, human operators, and procedural frameworks formed an interconnected system. Failure in one link triggered cascading effects. Flight 72 was not a story of one era, but of interactions between technology, humans, and environment. The aircraft's precision, the crew's training, and the calm night became the backdrop against which the sudden anomaly would unfold. It was an elegant system suddenly made unpredictable. At 11:40 a.m., cruising at 37,000 feet over Western Australia, Flight 72 entered the critical sequence. One of the aircraft's ADIUs began transmitting faulty data. Airspeed and angle of attack readings fluctuated erratically. The flight control computers interpreted these anomalies as a potential stall, triggering an automated pitch-down. The aircraft lurched abruptly. Passengers were thrown forward in their seats, shoulder straps biting into torsos, overhead lockers rattling. Alarms blazed, a cacophony of warning tones signaling flight control fault and Alpha PROT warnings. In the cockpit, the captain and first officer responded immediately, disengaging autopilot and stabilizing the aircraft. Yet the system continued to interpret erroneous inputs, and a second pitch-down followed within seconds. The sequence was brief, minutes in duration, but each movement compressed time for human response. Crew retraced procedures from memory and training, stabilized the aircraft, cross-check instruments, identify the source of the anomaly. Communication was rapid, precise, devoid of hesitation. The Airbus, normally predictable, now exhibited behavior outside standard parameters, challenging expectations and decision-making. Down in the cabin, injuries occurred despite seatbelts. Loose items became projectiles. Flight attendants administered first aid while coordinating with the cockpit. The coordination of human effort and automated system behavior was tested under pressure. Through 2 successive pitch-down events, the aircraft remained structurally intact. The crew's intervention, executed with calm decisiveness, prevented escalation. The Airbus settled back into stable flight, though tension remained palpable. Outside, the horizon returned to normal, the sun glinting off the wings as if nothing had occurred. Inside, a complex chain of errors, sensor, computer, and procedural, had been interrupted before reaching catastrophe. Flight 72 emerged from the incident without loss of life, but the event highlighted a critical lesson. Even highly automated systems rely on human judgment to intervene when technology fails. The sequence was not a crash, but near catastrophe, a demonstration of the fragile balance between human, machine, and environment. After the incident, Qantas Flight 72 landed safely in Perth. The immediate priority was medical. 12 passengers and one flight attendant required hospital treatment for injuries sustained during the uncommanded maneuvers. Beyond the human consequences, attention turned to the aircraft itself and the systems that had failed. The Australian Transport Safety Bureau, ATSB, conducted a meticulous investigation. They examined flight data recorders, cockpit voice recordings, and maintenance histories. The focus was clear. Why did the aircraft's sophisticated flight control system issue commands that endangered those on board? Investigators identified the fault in Adiru number 1, which intermittently transmitted erroneous data. The flight control computers, following program logic, reacted by initiating alpha protection pitch downs. The investigation highlighted the rare but significant potential for such sensor anomalies to propagate through automated systems, challenging the assumption that multiple redundancies eliminate risk entirely. Crew actions were analyzed in detail. The pilots had adhered to procedures, reacted promptly, and stabilized the aircraft. Their intervention interrupted the error chain, preventing escalation. The investigation praised their performance, noting that human judgment remained the final safeguard in highly automated flight. The impact of the incident extended beyond Qantas. Airbus issued procedural clarifications and software updates to mitigate similar Adiru faults. Airlines reviewed training protocols, emphasizing recognition of anomalous sensor behavior and rapid manual intervention. Aviation authorities integrated these lessons into guidance, reinforcing the principle that technology must be paired with vigilant human oversight. Flight 72's near disaster became a case study in automation dependency, sensor reliability, and human-system interaction. It underscored the importance of understanding failure chains, not assigning blame to single components. The incident reshaped thinking about redundancy, alarm management, and the human role in complex systems, leaving a legacy that continues to influence airline operations globally. Qantas Flight 72 was a wake-up call for the aviation industry. Even in an era of highly automated flight, vulnerabilities remained. The incident reinforced that technology, while sophisticated, cannot replace human judgment. Redundancy and safeguards are essential, but so is the skill and composure of trained pilots. Airbus responded with software updates to reduce the risk of similar Adiru anomalies. Qantas enhanced pilot training, emphasizing recognition of erroneous sensor data, rapid manual control, and cross-checking procedures. Flight crew simulation now routinely includes scenarios of sensor-driven automation anomalies, ensuring that experience extends beyond textbook procedures. Regulators integrated these lessons into broader safety guidance. Across the industry, procedures were reviewed, redundancy assumptions scrutinized, and human factors research intensified. Flight 72's story became a case study in system complexity, human-machine interaction, and the subtle balance of aviation safety. For passengers and crew, the incident left memories of sudden motion and unexpected alarms. For the aviation community, it left knowledge, procedural rigor, and technological refinement. Safety evolved not through catastrophe alone, but through careful analysis, disciplined response, and iterative improvement. In the end, Flight 72 reminds us that aviation safety is a living system, built on machines, guided by humans, and continuously learning. The Airbus A330 continued to fly safely, pilots continued to train rigorously, and passengers continued to trust that each flight carried them not only across distances, but within a framework constantly refined to prevent the improbable from becoming the inevitable. The skies returned to calm. Flight 72 had landed, and the lessons it delivered remained aloft, quiet, precise, and enduring.